So since I'm at RIT, I'd actually like to thank all of you for coming out here, particularly in the middle of January. You just missed a blizzard, so we engineered the weather just perfectly. So our technology's working. Some very exciting things here. So anyways, I'd like to point out my research group here at RIT and also highlight our primary collaborators, and you'll be seeing the work that we're doing with them, particularly at Air Force Research Lab, Dr. Paul Alsing and Mike Fanto, and at MIT, Dirk England's group. And I'd like to thank all of our sponsors down at the bottom. So what we do is quantum integrated photonics, so on a silicon photonic chip. So you've seen a couple examples of these, and I'm going to give an overview and then give details on some of the challenges that we're trying to overcome. So quantum information science obviously needs several things, just like any information system. You need a source of quantum bits. We need to be able to manipulate those bits and then ultimately store them so we can make a quantum computer or even a long-distance communication system. So ultimately, the best way to do that is to integrate it on a chip. For decades, people were trying to do it on big optical tables, but the scalability of that, particularly because of the probabilistic nature of quantum optics, has been challenging to do. So I think that's why a lot of you are here. So in terms of sources of qubits, there's different ways to do this, and this overview is in terms of general quantum. So you could have polarization states of a photon, a horizontal or vertical polarization, essentially, energy levels in an atom, or currents going in a superconducting circuit. So with that said, in terms of what they all share together to make them quantum, there's two things that you namely need. You need entanglement, and this is really for the students that are here. I know there's plenty of students here that are maybe still wondering what quantum is. So entanglement is where you have two particles, two atoms, and they're somehow essentially cannot be described independently. You can't tell them apart. So if you measure one of them in the ground state, you'll find the other one in an excited state, or vice versa. This is a very spooky sort of thing that can happen, but that's what is allowing us to potentially demonstrate these quantum technologies. The other is superposition. So in addition, you can have the atom in the ground and excited state exactly at the same time. And what that means is you're representing a lot more information with fewer physical elements. So if you essentially have two particles, you're representing 0, 0, 0, 1, 1, 0, and 1, 1 simultaneously. And that's why the scalability of quantum is so exciting. So with only 50 particles, you're equivalently representing 140 terabytes. We still don't even have that in our phones. So that's very exciting because you can do that with only 50 elements. So that's essentially why quantum is being investigated. Now, once we have those qubits, we need to be able to manipulate them, and obviously the focus of this talk is on quantum optics. So here we're showing examples of photonic circuits for doing that. So our collaborators at MIT, Professor Dirk England, they've demonstrated these photonic circuits with basic building blocks of beam splitters and put them together to essentially implement matrix multiplications. And if you put in photons that are in a superposition state or a quantum state, you can do essentially quantum matrix calculations, and that allows you to do much more than you would be able to do with a classical computer. Our own team here at RIT, collaborating with Air Force Research Lab, we've been implementing our own versions of these manipulation circuits. The one at MIT is a bit specialized, and you can see that in terms of the symmetry. Essentially, it starts large and gets smaller, whereas here we're trying to realize a full unitary matrix. So a little different take and a different application space. And then finally, you want to be able to store your qubits. Now, that's been the big challenge within the photonics community for many decades now. really the best way, at least our philosophy, is to make use of the best platform for doing that, which is essentially ions. So the talk that you just saw, we're really talking about essentially some sort of trap, surface trap with ions, because these are so stable that you can store a qubit for at least 15 minutes. And as a result, we want to be able to interface our photons in our chip with these ions, particularly the ytterbium ion. And that will potentially allow us to do things like create entanglement between two ions. And the way you do that is you have an ion up at the top, one down at the bottom. And the photons, the way that the ions essentially talk to the outside world is through photons. So that means we can entangle them together by sending the photons that get emitted from these ions into essentially a beam splitter. And our vision is obviously to do it on a chip. And I'll be talking later, a little bit later, about our work on photonic chips made out of aluminum nitride. But with that said, most of my talk is going to focus on our source of qubits. So I'm going to give you just a little bit introduction to how we do that. So one way that you can create photonic qubits is obviously if you have a single atom, or earlier this morning, Michael Lear talked about potentially using quantum dots. Here we're talking about doing it by using essentially nonlinear optics. So Professor Boyd, this is essentially his math from his textbook here, so I could have him walk us through, but pretty much we'll just go to the bottom here. And what you have is when you have a material, particularly a nonlinear material, and you put light into it, so so pointing here, you put light oscillating at omega. Essentially, you work through the math of the polarizability, and what you find is that what you get coming out of it will be oscillating at 2 omega. Now, in this case, we're just essentially doing this process in reverse. So we're sending into 2 omega, and then we get 2 omega photons out in order to meet energy conservation. So that has been done for quite some time, and the name for this is called SPDC, which stands for spontaneous parametric down conversion. So you have a nonlinear crystal, in this example, one that is type 2 phase matched, and you essentially put a UV laser in, and then you get 2 infrared photons coming out of it. And by tuning the phase matching, you can end up with them separated, or you can actually end up where you get 1 photon here and 1 photon here. And the important thing is each one is this one is horizontal, that one's vertical. So when you put these together in those points right there, you actually end up with polarization entanglement. And that's been a workhorse for decades, but obviously has to be done on an optical table. Those of you that know who I am, I've traditionally been a silicon person, and for good reason. That's what essentially every microchip is made out of. So I'm a big believer in being able to integrate electronics with photonics. So that's why we've chosen for some time to look at silicon. Now, unfortunately, silicon doesn't have this second order term that you see here. It's 0 in silicon. With that said, there's some tricks you can play to do it, but the vast majority of demonstrations have been done with the third order nonlinearity, which is really similar to the second order that you'd have in a typical nonlinear crystal, but you just need one more pump laser because you need one more wave to interact. But if you look at it, really it's similar. You now have 2 pumps, and then you get these photons getting produced. And I'll be talking about this circuit a little bit more in a second. So we've been working on this for a while. So we started with the traditional Chi2 spontaneous parametric down conversion on an optical table like you see here. This is Mike Fanto at Air Force Research Lab, and used very big Ti-sapphire lasers to pump them. Then we've done work to integrate it onto a nonlinear chip, so KTP, or periodically poled lithium niobate. But ultimately, in order to have really high scalability that you need, we really believe you need to make use of silicon. So that's exactly what we have here. We have silicon photonic chips made through AIM Photonics, where we have hundreds and approaching thousands of individual components. So we can have lots of qubits in a very, very tiny chip, and potentially very cheap, particularly if we use the internet as our laser, like was noted earlier. That's a very cool idea. And then I just want to touch on, we're also working on UV compatible versions. Unfortunately, you can't use silicon. Silicon is opaque in the UV. So we're implementing the ideas that you're going to see here also in aluminum nitride because it has a very large band gap, so we can interact with ytterbium ions. So in terms of the silicon photonic platform, I haven't gotten into the nuts and bolts of it yet. So basically what you have is a waveguide, just a rectangle of silicon, and all you do is put a laser in there. I just want to reiterate that point. You could essentially just take light out of the internet, send it in here, and you're getting photons essentially for free coming out of this chip. So here is that again, just with a little bit more technical details. So the light in the silicon waveguide essentially looks like this. This is called the optical mode. So that pump laser, which pump usually is taken as a term meaning that you need a lot of light, but silicon waveguides are so small that you're able to, with only even nanowatts we see it, you're able to actually get a very strong nonlinear interaction that is producing plenty of photons. And even a milliwatt would even be potentially too much because you start to get multi-photon generation. So it really is a very efficient platform for producing individual photon pairs, a signal and idler like I have here. Another advantage of silicon is it's relatively low noise. So work has been done on using silicon nitride, for example. But the challenge with silicon nitride is it's an amorphous material, which means there's a lot of Raman scattering that's undefined in it. Whereas in silicon it's a crystalline material, so the Raman scattering is very well defined, and you can very easily filter that away, basically about 100 nanometers away. And then the great thing with silicon is we can make very tight bends, so that means we can make resonators with very high finesse, or you usually might think of it as Q. So we've been working on this for quite some time now, so I'm going to show you some of our early results just to kind of get you into what we're doing, and then the challenges that we're trying to essentially solve with this. So we have a chip with waveguides and individual ring resonators, so that's looping a waveguide on itself. Here's the parameters for the sizes, and there's a very small gap between the rings so the light can couple in there. So whenever light is a wavelength is a multiple of the circumference, then you have these resonant dips that you see essentially right here. So what we do is we tune our pump laser here externally to one of those resonances, and by virtue of just putting that light into the resonance, you're going to just generate signal and idlers by the fact that you have energy conservation. And what's important is to make sure that you have a resonance at a signal wavelength and an idler, and it will basically take care of itself automatically. So we send that in, we generate signal and idlers, but then we need to separate them out. So in order to verify that we actually are producing these two photons, we essentially need to use two detectors. So what we do is, on the previous slide, we split them spectrally, as you can see right here, that one there and that one there. And then we send them into essentially a fancy stopwatch. So we send one here. This says switch to using the mouse pointer. I may use that. It's a little slow. Or somebody moving my mouse? I don't know. Okay, so basically a fancy stopwatch. So you send one photon here and then another one here. And I say fancy because it's just very, very fast. It's able to discriminate events on the order of a few picoseconds, as you can see there. So if we have two photons, then essentially we're going to have a peak. If it was noise, we would not see a peak like you see here. And the important metric is essentially the signal to noise that you would have with these photons. And the name for that is called the coincidental to accidental ratio. So noise would be accidental counts outside of that peak. We want to have coincidences. We want them to both be coming in at the same time. And we essentially want that ratio to be as high as possible. And over 5 years ago, we were measuring cars. I'll keep calling it a car, not the one you drive, but essentially signal to noise of over 2,000. But obviously, it depends a bit in terms of how you define where you measure this car. So if we narrow it down that we're only looking at the peak, you can actually claim a car that's much higher. So there's not consistency in the field with how this is defined yet, and that's something I would like to see, or at a minimum be providing plots like this so you're not artificially inflating essentially what your signal to noise happens to be. So that's my point there. And then we can actually look at the photons that are being produced. So we put a filter external to the chip and essentially spectrally look at the photons, and we see that they are very narrow. So that also tells us that the resonator is actually generating these photons in the first place. So then we can change our power that we're looking at it, and if you go back to the theory, you'll essentially see that you should observe that the photon counts scale with the square of the power, but then there are noise processes. I said earlier that you wouldn't have Raman noise, but the silicon waveguides, they're fully embedded in glass. And also you have optical fibers, and that produces Raman noise. So you always have a Raman signature that is going to be around there. So Raman noise adds, and then the detectors are imperfect, so you have dark counts. So we can, in the blue, we've plotted our direct measurements, and then what we can do is we can look at the coincidence of the photons. So when we detect two photons, because our car is so high, we have high confidence that those two detections came from our ring resonator, and we can calculate essentially our guess as to how many photons are actually being produced, and you can see we have good agreement between what's raw measured versus essentially fitting this theory. Okay, so in the previous, I showed the case where we used one pump laser, and you ended up with two photons that are at different wavelengths. Well, you can actually do the process in what I call reverse, or degenerate pairs. So we can have two pump lasers at those two separate wavelengths, and in that case, we actually will end up with two photons that were at the original pump wavelength, but now they are identical. So we get biphotons. So we have a way to essentially deterministically create exactly two photons at the same frequency. So the experiment otherwise is pretty much the same. So we see similar results as before. So we have the two pump lasers now at the two resonances at the side, and we get the biphotons. But you might notice the car is quite a bit lower, essentially order of magnitude. And the reason for that is the process is pretty much completely random. You don't know when it's going to happen. And then each pump laser obviously can act on its own. So this pump laser would be producing a signal in idler that's non-degenerate, and that one right there would do it. So what you end up with is essentially unpaired signal in idler photons on top of your central biphoton, which brings up your noise level, so that's why your car should go down. So that's a potential disadvantage of maybe producing biphotons in the first place, but the advantage of them obviously is they are at least identical in terms of frequency, and that's very important if you want to be able to scale up your quantum system. And I just want to show that those biphotons, if we scan the pump laser about the two pump lasers about the resonance, you see that the generation rate, that's the heat map that you see here, obviously is very tied to having both of those lasers, pump lasers, on resonance. So what we've done is we've taken this photon source and integrated it into an interferometer to demonstrate that when we produce biphotons, so we're getting two photons at the same time, we can immediately essentially cause a quantum effect. So when you have two photons, that's a quantum state. And as a result, you should start to see some quantum phenomena. And the easiest thing that we can do is do something called quantum interference, or two-photon interference. So this is our setup here, and now here is more detail on the device. So we use two pump lasers, and you see we have a little more complicated circuit here where we split the two lasers into two, so both of them are now going to be going clockwise and anti-clockwise. And what that means is we're going to be pumping in both directions at the same time. So we need to introduce just a little bit of math to understand what we're going to get. So the creation of a photon looks like this. So you start from nothing, vacuum, and then you get a photon. If you produce 2 photons, this is what the math looks like. You actually end up with a phase of 2 theta, and that's the most important point. And now if we take into account the situation we have here where we're pumping both clockwise and anti-clockwise, that means that you get a superposition state where you have 2 photons that are going clockwise or 2 photons that are going counterclockwise. And the important point is you see they're oscillating at 2 theta. So in classical optics, you would see an oscillation at theta. This is quantum, so we see that is going to oscillate at 2 theta. Oh, and how do we control the theta? So when the photons come out, so we either have 2 over here or we have 2 over here, we tune the theta by tuning this arm. So all we've done here is spiral the waveguide up. You might be trying to follow what's happening there. All it's doing is we're just trying to put it in a smaller space so that when we heat it up, we're able to do that easier. So the top is showing the pump lasers. So this is classical. So obviously, as we change the phase, we'd see the pump lasers going through constructive and destructive interference. But then when we look at the 2 photons, by just having 2 detectors and look at the coincidences, we see that it oscillates twice as fast. This sine wave is twice the frequency of that one. So that proves that we have 2 photon interference coming out of just a single device. Other demonstrations required 2 individual resonators. Here, we've done it in just 1 device. So you already, from a very simple circuit, are able to do some quantum experiments. And one thing that we wanted to look at to ensure that what we're seeing here is really from 2 photon interference as opposed to maybe the pump lasers somehow doing this on their own, what we did was, this was a situation we were pumping and we were getting photons in the middle. What we did was simply, so that's what we would expect. We were looking right there. If we move one of the pump lasers, now, just because of odd multiples, we wouldn't get any photon generation on that resonance, or biphoton generation specifically, and we end up with this incoherent signal that you see here. So we know that we're definitely seeing interference of those 2 photons, and that actually shows a cool trick that you could do here. You could potentially pick any of these as long as they're symmetric about that point, and that's what we did. We pumped there, and you see we keep seeing this interference over and over. Now the visibilities are not great, and a big reason for that was this was made using in e-beam lithography in a university clean room. We didn't have good directional couplers and such. Yeah, thanks. Okay, so now the last part of this talk. So the photon source, I think I've proven that we're able to produce these photons, but this photon source actually has a big problem. Basically, most of the photons that are being generated are actually not useful. Most of them are being lost. And you can see that from this picture here. So we have 4 situations. Essentially, we're pumping, and you see that we have 4 possibilities. The 2 photons, the signal and idler, they could both come out this way. They could both come out that way. One could go this way. One could go that way, and vice versa. So in our circuit, we probably only care about the case where they are going in the direction that we want our circuit to go. That is a big problem because everything's probabilistic as it is. If we're losing all these photons, and they can end up essentially increasing our noise or just our efficiencies aren't very good. So a very common metric that people use is this thing called heralding efficiency, which is essentially the ratio of whether you actually get a coincidence that they both went the way that you wanted relative to essentially whether you produced it. But this is a very hard thing to measure because you don't know how many are actually produced in the first place. You have to essentially back out insertion losses. So we are strongly advocating for the use of a metric called coincidence efficiency, which simply just looks at the coincidences that you have relative to the coincidences you'd measure in all possibilities. Obviously, you need to be able to do that. And then this gives a little bit into the idea of how we can potentially engineer this. So here is a bit more complete model of the ring resonator source. And essentially, you see that we can maximize our coincidence efficiency if we make this coupling here, or in other words, we make this coupling much bigger than the coupling into the ring. So if this coupling is very weak, we won't get the photons coming out there. But that comes with a big trade-off. We need to be able to get the pump in there in the first place in order to do it. So as a result, yes, you can get all the photons going the way that you want them at this drop port, for example, but you need to essentially use infinite pump power to do that. So we looked at this by literally just changing the distance of the input sequentially through here. That would mean that we're going to have a harder time getting the pump into there, but we'll see the photons go the way that we expect, and that's exactly what we see here. So this is a symmetric case where we see all four possibilities are roughly about the same. And then the case where the input gap is very large, we see essentially all the photons are going out the drop port just through, if you just read this real quick, I'm running a little low on time, is just a background signal. So we essentially see, though, that we don't have any cross terms anymore, which means all the photons are going the way that we want, but it comes at the cost that we needed to use 10 times more power to pump it because we couldn't get the pump laser essentially into there. So right around when we saw these, got these results, we saw this theoretical paper come out from University of Toronto and University of Pavia, where they talked specifically about this trade-off, that you want to be able to pump the source and generate lots of photons, but you also want to be able to get them to go where you want, essentially heralding. So this is a big dilemma, because in order to generate lots of photons, you want a resonator that is critically coupled. That means all of the pump light is going into it. But from the standpoint of the photons that you're trying to produce, you want to get them out of the resonator as quickly as possible so that they're not lost in the resonator or go elsewhere. You want them to all go one particular way. So as a result, this is pretty much impossible to do when you just have a single bus ring resonator. But with a dual, we have a chance. And the way that we do that is make a slightly more complicated ring resonator where we actually control the coupling going into and out of the ring independently. And the way you can think of this is you have a Mach-Zehnder interferometer integrated with the ring. So with a Mach-Zehnder interferometer, you essentially have places of constructive and destructive interference, and then with a ring, you have resonances. If we put these two ideas together, essentially, and get the length of the Mach-Zehnder just right, you can end up with a situation where you are inhibiting resonances, and as a result, we have, instead of all these resonances, we can end up with only every other resonance because of the interference that we have from this interferometer. And then we can do this, we can put another interferometer on here meant for the photons that we're generating, and that allows us to now have two independent controls. We can have our pump come in critically coupled, and then we can have our photons come out whenever we want them. So we fabricated this through AIM Photonics, and on the left is the initial configuration. So unfortunately, as many of you know, when you make these things, they don't come out exactly how you would expect them. So you need to heat them in order to get the phases just right. But once we do that, and that's the great thing about having integrated photonics, we get the configuration that you want. Essentially, the pump is critically coupled. You see that here, you don't see from the pump side the resonances where we're going to get our signal either. And from the output side, we do have those resonances. So that means that we generate the photons here and we get them coming out. And the net result is in the initial configuration, we have very poor results. Photons are coming out all of the different ports, and you actually see the generation rate is quite low. But on the right, after we tune it, you see we have order of magnitude higher coincidences, and more importantly, you don't see any cross terms. You actually see they're essentially in the noise. So we're directing all the photons where we want them, and it's critically coupled, which means we're getting the best of both worlds. So we essentially do have a free lunch, ultimately, with this. And we can control it, and I'll just have one last slide right here. We can do this from the standpoint of getting very efficient heralding, but with our collaborators at Toronto and Pavia, they looked at using the same in order to create unentangled photons, which is actually more important from a heralding standpoint. So by tuning this in the right way, we can end up with a joint spectral that is between the signal and under photons that there's essentially no correlations. And that's exactly what you want, because you want to be able to detect the idler and then use the signal photon for your actual quantum circuit. So thank you. Sorry for going a little bit over.
We do have time for a couple of quick questions. Anyone has a question? Yes, sir. What was that?
Microphones.
Yeah,
somebody's coming.
There's one coming right behind you.
So it's great. You have this extremely high coincidence efficiency. That's fabulous. So what is, though, the actual efficiency? Coincidence over singles rate, certainly you can measure it. It may not be good, but you could certainly measure it.
Yeah, so as I said, I'm skeptical of those numbers because you got to back out all these different losses.
No, don't back out anything. Just what's the coincidence rate divided by the singles rate?
Oh, the coincidence? I'd honestly, I'd be making it up off the top of my head. I'd have to look it up, but I can do that offline if you
Okay.
want. Yep.
Is there another quick question for us? In that case, let's thank him again.
Thank you.